It's always freezing in this room. I have so much adrenaline when class starts. I'm just so cold.
It's cold in my room too.
Oh, it's terrible. A window, yes. This one. Share. Make sure I'm oriented properly. There we go. You know what? Every once in a while, my visualizer goes black, and I don't know why. This is not good. Hold on. Maybe I'll restart it and see. Sometimes it only happens when I like just connect it though, and this has been connected for a long time. Yeah. Let me try to reconnect it. I don't know. If something ever happened to my document camera, I'd be in major trouble because you cannot buy these anymore. Okay, I'm gonna try one more time. There we go. Okay.
All right.
4. All right. Is it, what kind of problem is it, Mia? Tell me.
It's one of the ones where it's hard to explain. You have to simplify it. So I'm sorry.
Expand or condense?
You have to condense it.
Okay.
Yes. And then it was like, what is the problem set? And then I did it, but I don't understand how they got the answer to it.
Okay. Well, tell me what it says.
So it's log base 2, and then in parentheses it has x minus 5.
Okay.
And then plus log base 2, and then in parentheses x minus 3.
Okay.
And then minus log base 2 equals 3.
Oh, wait, minus log base 2 of what?
I must have written it wrong because it isn't of anything. I just wrote it as log base 2.
Is it just of x? Maybe you forgot the x.
Likely.
Do you have the 3-digit number that this was based off of?
No, I do not.
Okay, let's see. Let me see if I can figure out where it came from. All right, expand, condense. I don't even see one that matches this in the book. But it was from 4.3?
Yeah, I believe so.
You don't have anything?
You kept asking me to find the problem set.
Oh, you said
it
equals 3?
And then it equals 3.
Well, then it can't be a condensed problem. It must be from 4.4, no?
I think you're right. Yeah, it is from 4.4. Kept asking.
Asking you to find the solution set.
Yes.
Okay.
But I got stuck up when it was asking me to find that problem set. And it was like, oh, don't solve for x. Simplify it and do the problem set.
This to me looks like 4.475. And 4.475, I'll put it up here to show you what it looks like. Remember that my math lab has to match your book problems, and 75 was probably assigned. I mean, I can double check, but this is what it looks like to me. It's got log base 2 of an expression plus log base 2 of another expression minus log base 2 of x equals.
Yeah, that was most likely it.
Okay.
Or something like that, yeah.
Okay. Well, we'll do this one, and then if you feel like, wait, that doesn't look like what I saw, then let me know. But these are all logs only. And this is the only one I see with addition, subtraction, and a number.
All right.
Okay. So let's do this one. All right, so this would be solving an equation. So you're right, though, that we would need to condense in order to solve this equation. So we're going to start out by condensing these logarithms into one log. And our goal here is to get this into log base b of, what did we say, c equals m? I don't remember what variables we used, and I don't want to change them because that will really confuse people. Log base b of m equals c. That's right. Okay. So in order to do that, we need to get this written as one logarithm. So we're going to start working left to right, and we'll combine the first two first. And since you have the sum of two logs, you can change this to the log of a product. So we're going to change the first two terms to be log base 2 of x minus 5 times x minus 3. And then we'll worry about the rest of this last term in just a minute.
All right.
So from here, we'll go ahead and FOIL this out. You have x squared minus 8x plus 15 minus log base 2 of x equals 3. Let's see what's happening on here. Was this a problem in the homework on my math lab? Yes, Sebastian. Mia was asking about this problem that she had on her homework, and you had a similar problem. I don't know which one it was on the homework, but it should be, it should have the 3-digit code 4475. That's all it could be. Okay. All right, so we're this far. Now you have subtraction. So you have the difference of two logs, and when you have the difference of two logs, you're going to write this as one log using division. So in the numerator, you'll have x squared minus 8x plus 15. And in the denominator, you'll have x. And then we'll set this equal to 3.
All right.
Questions so far on the solution process?
Not really.
Okay.
So far, that's what I was doing. But
Okay.
when I solved it, I put I guess what the base was, I had it equal to 3, and I don't understand where they got that exponent from.
Okay. So you should be, in order to get from your log form to your exponential form, remember that you're going to take the base to the exponent and set it equal to this log argument m. So we're going to switch the log form now to exponential form. So we're going to take the base to the third power and set it equal to this expression on the right-hand side.
Oh.
That's the trick. So condensing it down, this will get you a lot of points on your exam, but maybe half the points, because there is a lot of work involved. It's just that you haven't actually solved the equation yet.
So that's how they got rid of the log.
Yes, yes. So we're changing that to exponential form. Okay. So now we'll simplify. 2 cubed is 8. And you can do this in 2 steps or 1. But now that we have 8, we can go ahead and multiply both sides by x to get rid of that denominator. So you have 8x equals x squared minus 8x plus 15. And be careful here, because some of you will maybe see 8x and 8x and you'll be like, oh, cool, they cancel out. But that's not true, because if we have a quadratic equation, we need to get it set equal to 0. To get it set equal to 0, when you subtract 8x from both sides, you get minus 16x plus 15. Okay, any questions here? Okay, and now you're going to go ahead and factor this. The two numbers that multiply to positive 15 and add to negative 16 are negative 15 and negative 1. So that means initially you have x equals 1 and x equals 15. You're going to have to go through and check. Just because I have the teacher's manual here and it only lists one solution, I know that one of these is not going to check. So let's see which one it is. All right, so one of these is not going to work. 1 and 15. Notice that if you let x be 1, 1 minus 5 is -4, and you can't take the log of a negative number. So it won't work here, and it doesn't even matter if it works anywhere else, because at this point, it's already violated the domain over here. 1 minus 3 also would violate the domain there. So it must be the case that x equals 1 cannot be a solution. So you need to go back and check 15. 15 minus 5 is positive. That's good. 15 minus 3 is also positive. 15 itself is positive. That means that 15 does not violate the domain, and that's your one solution. Someone had asked last time, what if we check both of them, and both of them are no good for the domain? If that's the case, then you have a no solution situation. You probably saw maybe at most like 2 of those on your homework. Well, you could have maybe seen 3, but you probably didn't see 3. Okay, other questions on that one or other equations that you were solving for your homework? Okay, anyone else? Okay. Okay, nothing else? All right, okay. Well, I do plan to review a little bit more today. So hopefully if there are any questions that people are hesitant to ask, we'll hit those in the review. There's one that I put in the review that Nancy stuck around and wanted to see after class last week. And as soon as I gave it to her to work on as practice, I realized like, oh, I really should have gone over one of these in class. I want to make sure we get it in the review today because I think it'd be really helpful for you to see it. As far as what we're doing today, we're going to talk about exponential growth and decay. It's a pretty short section, 4.5, and this will be the last section that we're covering for your chapter 4 test. It's the last section in chapter 4. And we had talked about whether or not we might want to have our test Wednesday or Monday. I really suggest you get it out of the way Wednesday, especially since 4.5 is a pretty short section. It's not going to take us very long to get through it, and it's a lot of stuff that we've already done, just kind of applying it to growth and decay models. So let's see, you know, I have this heater on, and for some reason I'm paranoid that it's on fan because I can't stop freezing. Go check this. Make sure I'm not like freezing myself. Okay, it's on heater. I'm like shaking. I'm so cold. Okay. We're going to model exponential growth and decay. You know, I was going to say something else, and I totally had lost it a moment ago, but now it's back. I was thinking that maybe we don't have a lot of homework questions because we're not doing the homework. And I've meant to harp on you for this before, and I keep forgetting to. Some of you aren't doing homework at all. Some of you started out doing homework and then you recently stopped. Others maybe do an assignment here or there and then you don't do it. I've noticed that we tend to do the homework at the beginning of a chapter, and towards the end we stop doing it. Sometimes students are like, yeah, I don't do the homework because there's too much homework. If you feel like there's too much, then just do whatever you feel is appropriate for you and then stop, because at least then you'll be getting some points for it and not 0 points for it. Homework is, and I'm going to double check this, because I changed it this year since we're remote. It used to be 20% of your grade. Pretty sure it's 15 now. Double check before I say that. 15%. No, 20%. It's still 20. I dropped the exams down to 55. They used to be 60. And I dropped the final exam from 20 to 15. So that's what happened. And I took the 10 and put it on quizzes. Your homework is 20% of your grade. Now, it may seem like 20% is not that much. It is a lot. Imagine if you would have done all of your homework and you would have gotten all of the points for it, because a lot of you who do the homework, you get 100% on it. That could potentially take your grade from like a 75 to a 95, or from a 60 to an 80. That's 20 points onto your total of 100 points in the course. It makes a huge difference. So for those of you who aren't doing your homework, that is really, really detrimental to your grade. You know, I say this all the time. It's so unfortunate. I'll have students who get just B's on all of their exams, and yet if they don't do well enough on their homework, and I mean, they could end up failing the class. And it's very unfortunate because clearly they know what they're doing. They're just not doing the homework. And I can't just pass you because I feel like your exams were good. You have this in your syllabus. 20% of your grade is your homework. It should be the easiest 20% of your grade to attain. I mean, most of you wouldn't just skip a quiz. You wouldn't just skip a test. So why would you skip your homework? I don't get it. And not only is it points that you're going to get for your grade, but it's practice so that you will know what you're doing come time for the exam. I never understood why anyone would skip their homework. I just don't know. But anyway, it's becoming a little bit more of a problem. So I wanted to make sure we discuss the importance of homework so that you don't feel like it's nothing. All right. Back to this, growth and decay. Okay, the mathematical model for exponential growth or decay is given by f of t equals a sub naught e to the kt, or a equals a sub naught e to the kt. Now, you might be wondering, why is the model the same for growth and decay? That doesn't make any sense. Well, the difference will lie in the value of k. So if your value of k is positive, then the function models the amount or size of a growing entity. Now, we kind of talked about like a quantity a sub naught last time, but when you see this, this little zero that looks like it's in a base, this is a sub naught. That's the original amount or size of the growing entity at time t equals 0. So similar to when you were doing those investment problems and you were talking about the principal being your original amount, that's pretty similar to what a sub naught is here. This is the amount at time, and a is the amount at time t, and k is the constant representing the growth rate. If k is less than 0, then the function models decay. We still have a sub naught as the original, or the original amount or size of the decaying entity at time t equals 0. A is the amount at time t, and k is the constant representing the decay rate. Now, thinking about the fact that this k is in your exponent, you should be able to kind of intuitively think about what these graphs look like. If the value in your exponent is positive, and by the way, t can't be negative, so the only thing that would cause it to be negative or positive is k, then your graph would be heading up and to the right because you're just looking at this exponential function with that positive exponent. If k is less than 0, meaning k is a negative value, anytime you make the inside of the function negative inside that exponent, you're flipping this about the y-axis. So it's kind of reflecting about y. And then you're going to get this behavior where the graph is heading down as t gets larger and larger. The value of f of t will decrease over time exponentially. So that's what the graphs look like. We might spend a little bit of time looking at the graphs, but very likely we're just going to be going through some of these application problems so that you understand how the growth and decay models work. You'll probably see these again in calculus. Most of the time we do talk about these in Calc 1, so you'll hit this again. All right, questions before we begin? Okay, wonderful. Okay, number one, the value of a particular investment follows a pattern of exponential growth. In the year 2000, you invested money in a money market account. The value of your investment T years after 2000 is given by the exponential growth model, A equals 5100 e to the 0.057 t. How much did you initially invest in the account? Now, there's barely any space here, and that's by design. This is not something that you're supposed to really think hard about. This is just, can you interpret the function for the growth in your account? So this is just based off of the growth model that you're given. Remember that your value A sub naught is this constant in front of the exponential expression. So that means that A sub naught equals 5,100. So it must be the case that the initial investment is $5,100. So for that, don't make it harder than it has to be. The initial amount is always just going to be this constant in front of the exponential expression for your growth function. So the next question is, how long would it take to have an accumulated balance of $10,000? Now, remember, going back to your definition, A is the amount at time t. We're trying to figure out time t, but we know the amount that we're looking for, which is A. And this should be a little bit more intuitive to you because it is pretty similar to the interest problems that we did in the beginning of the chapter. So we're trying to get our accumulated amount, and I'm going to rewrite the function one more time down here so you can match it up, to be $10,000. And it started out at $5,100. So if we're trying to answer the question, how long would it take? That means we're trying to solve for t. So your question is always going to lead you to what variable you're trying to solve for. All right, so here's your final amount, initial amount, and then you already have this growth constant k in your function. We're just trying to figure out the value of t for how long it would take for your account to obtain that amount, that value. In order to solve for t, we're solving here an exponential equation. That means we need to get the exponential expression isolated on one side of the equation. So the first thing you need to do is divide both sides of the equation by that constant multiple that's in front of your exponential expression. So we're going to take 10,000 and divide it by 5,100. And I'm going to leave mine as a fraction just because, or I want to at least leave it exact because I'm going to want to keep as many digits as possible. So I at least know that I can get rid of 100 there. And then I can say 100 over 51 equals e to the 0.057 t. And I'm going to tell you what I tend to do often where I make a mistake on these. When I rewrite them, sometimes I forget to include like a leading or the zero that's in the tens place, because I'll write this 0 in front of the decimal point and then I'll forget to write the second one. Just be careful and make sure you have all of your decimals where they're supposed to be and any zeros where they're supposed to be. It's a very easy thing to miss. Are there any questions so far? Okay. All right, so now we're trying to solve for t. In order to get t out of the exponent, we're going to have to apply a natural log. Remember that we cannot solve for t as long as it's in the exponent. We have to pull it out. And we're going to put a log in front of it so that we can pull the exponent down in front. So I'm going to apply a log to both sides. Natural log 100 over 51 equals the natural log of e to the 0.057t. And now we can simplify the right-hand side. Remember, the natural log of e to the x is just x. What that means is that I can just take the exponent out now. So we have the natural log of 100 over 51 equals 0.057t. And notice that I keep just pulling my fraction along here, 100 over 51. I'm not calling it 1.96. I want to make sure that I have the exact value so that when I'm ready at the end, I can use the exact value to find t. Don't want to have any rounding errors. Now to solve for t, we're going to divide both sides by 0.057. So now you can go ahead and take your 100 over, or I'm sorry, we're going to need a natural log. I'll just put my calculator up here. The natural log 100 over 51 divided by 0.057. Make sure that you close off your natural log. You need the second parenthesis in here before you divide. And I get approximately 11.8. What did I say to round to? I did not say. So I think if we're talking about years, maybe 11.8 years is fine. I would specify if I wanted a particular number of decimal places. So right now we're just solving an equation like we've done before using the growth model. But we're going to do a little bit more with that growth model next. Before I move on to the next problem, does anybody have a question about this one? Okay. Oh, good. I was just about to say, I'm worried that people have questions and they're not asking. And then I heard the chat and it was Beth saying no. All right. Are you sure we don't have any questions? Does anyone other than... No, okay. Wonderful. You know, I had my settings so that I could see. I don't know. I always forget how to find this. That's okay. I'll look later. Oh, there it is. Like you have to change this every time. You know, I like to see all the little squares that have everyone's initial on them instead of seeing their faces. Just kidding. Feel free to turn your camera on. So I'm seeing more than one person or more than two people. Is that just a pipe dream? It's a pipe dream. Am I becoming disillusioned? Yes. No. You know, we're at midterm. Everyone's just kind of tired and remote learning is not fun. And now we have all these new COVID restrictions. Oh, man. My mom was like, oh, I went to Denny's on Saturday and all of a sudden I couldn't eat inside again. And we had to order carryout only. And I laughed at her and was like, ha ha, your region was really bad. Come to Suburban Cook and you can eat in a restaurant. And then today they were like, Suburban Cook is getting hit with COVID mitigations. I'm like, oh man. Next thing you know, my kids will be out of their hybrid school, back home 24/7. Terrible. Okay. King County be like what, Mia? King County be like closed down. Yes. Yes. I know. I will look really forward to date nights all winter trying to eat in one of those tents with the little heaters underneath. It's really terrible. All right. Anyway, as I was saying, back to math. Number 2, the function a equals a sub naught e to the negative 0.01155x models the amount in pounds of a particular radioactive material stored in a concrete vault, where x is the number of years since the material was put into the vault. If 700 pounds of the material are initially put into the vault, underline that initially, that should be a keyword for you. You're thinking a sub naught. How many pounds will be left after 170 years? Years represents time. That's going to be your T. So you should be picking out these values as you work your way through. So 700 pounds are initially put in the vault. How many will be left over after 170 years? So that is the final amount, A. So you have your equation. A sub naught is the initial amount that were put into the vault. Did I say account? I meant vault. 700. We've been talking so much about accounts. That's our initial amount. E to the negative 0.01155. And then remember that you were told X is the number of years since the material was put into the vault. So that would be 170 years. Now I called it T. Technically that should be time, which in this case is X. Now again, you were given a little amount of space to do this one, a little bit, because this time you're not trying to solve an exponential equation. You're just trying to evaluate an exponential expression. So you can put this into your calculator as 700 times, did we talk about our E button? I think we did last time. If you're not sure where your E button is, it's second natural log. That will bring up your E. I think we did talk about this like a week ago. E to the negative 0.01155 times 170. And I get approximately 98.26. And now you need to ask yourself whether or not that answer makes sense. Let's see, do I have rounding instructions? No. So we'll just put 98.26. And don't forget to label your answer. We're talking about the number of pounds that will be left over. What I mean about does your answer make sense is you need to ask yourself if this sounds right to you. Initially, you were told that we had a particular radioactive material, and you started out with 700 pounds of it. Now, the radioactive material, if you're not familiar, it's going to decay as it sits in there. It's not going to get stronger. It's going to decay. And if you're not 100% certain about that, look at the fact that K, your constant here, is negative. So because K, that decay constant is negative, that tells you that this is going to be getting smaller. So you've taken now the 700 pounds and reduced it over 170 years down to 98.26 pounds. So really you just want to make sure that if it's some sort of a decay, that you're actually being shown that the value is decaying and a value that makes sense. Obviously it can't be negative. So just be careful about that. Are there any questions on number 2? Ooh, I hear a beep. Is it just Beth saying no? Okay. To what number in the decimal do you want us to round to? If I don't say, usually 2 is a pretty good value. And I'm really glad you asked that, actually, Sebastian, because a lot of times I don't want you to round at all. And a lot of the time on your test, especially if you're just solving an equation, I'm going to say, don't round your answer. But when it's an application problem like this, I do want you to round your answer. But on a test, I will specify the number of digits. And your My Math Lab homework will also specify If on the notes I did not specify, I usually just go with 2. My math lab will either want an exact answer or it has to tell you the rounding instructions, and it should for this book because this book is extremely well vetted. It's an extremely popular book and it's been out for years, and pretty much any issue with it has been reported and fixed long ago. But if you feel like you're not sure, go to the help aids and hit the Ask My Instructor button and send it to me, and then I'll send it to them and they'll fix it. But it'll usually say in the blue instructions underneath the box, those are the input instructions, it'll tell you what to round to. And if you don't have rounding instructions, it's assumed to be an exact answer. So yeah, and I think with the homework you guys were working on, there probably weren't rounding instructions because they were probably mostly exact. Okay. Wonderful. Now, let us move on to number 3. I really like number 3 because it's a very useful problem. The half-life of silicon-32 is 710 years. If 30 grams is present now, how much will be present in 300 years? Now, this one is a little bit tricky because it's a half-life problem. Now, you will see a couple of these on your homework. You're going to do half-life problems always the same way. Now, I'm going to give you the general formula for this, but I'm going to derive it for you first. So going back to your initial equation here for growth and decay, you have f of t, or we'll just use the a in this case, equals a sub naught e to the kt. So that is on the first page of your notes. Went there and got that out there for you. Oh, it's okay, Ben. I thought you were just bored of my talking about COVID restrictions. Okay. A equals a sub naught e to the kt. Now we're talking about half-life. Half-life means basically we're looking at how long it's going to take some sort of material to decay down to half of its current value. Now, if we want the end value to be half of the initial value, then we want A to just be the initial value divided by 2. Let me expand this note here. Half-life means the final value is half of the initial value. Okay, so we want the final value, which we normally call A, to be half of the initial value, which is a sub naught. So we're just going to let the final value be a sub naught over 2. Now, if you want to think about it this way, you could write this as 1/2 a sub naught equals a sub naught e to the kt. And you would just be writing the exact same thing, but using a coefficient of 1/2 instead of showing division by 2. And then you could divide both sides of the equation by a sub naught. And then guess what? All you have left is 1/2 equals e to the kt. So this is your half-life formula. You might want to highlight that, put a star around it. Sometimes students like to put clouds around important things. This is your half-life formula. Sometimes half-life problems can be tricky because a lot of times they involve 2 steps. So make sure that you have this well noted. Does anyone have a question before we use this formula about how we obtained it? Okay. So we have 1/2 equals e to the kt because we know we're talking about half-life. We know that the half-life is 710 years. Now, looking at your formula, we have a t that we need to replace, and we also have a k. However, I didn't give you any information about the rate of decay. All I told you was that the half-life is 710 years. Then I gave you information about a value then and a value now. So what you're going to have to do is 2 things. The first thing is you're going to use t to find k. You need to see that. First, we're going to use t to find k. Once we find k, we can get a general formula for silicone 32, and then we can talk about any value of t that we'd like. Okay. So we're going to use t to find k. That means that we're going to let t be this number of years that it takes for silicone 32 to become half of its value, which is 710. So we have 1/2 equals e to the k times 710. Now what we're going to do is solve for k to get that constant for the rate of decay. In order to do that, if I'm trying to solve for k and it's in the exponent, I need to get it out of the exponent. The only way I'm going to do that is by applying a natural log on both sides. So I'm going to take natural log of 1/2 equals the natural log of e to the 710k. You can multiply in any order, and we usually leave the variable on the back of a constant. And then we have the natural log of 1/2 equals, well, the natural log of e to the x is just x. So on the right-hand side, we just have 710k. And then to solve for k, we'll divide both sides by 710. And we have k equals the natural log of 1/2 divided by 710. Now, this is sort of a preliminary solution because it doesn't actually answer the question, but we need it to answer the question. So this is the rate of decay. Now, I know what you're thinking. Shouldn't we get a decimal approximation for this? No, we want this to be as exact as we possibly can. And I know that's annoying because it means you have to carry around a lot of extra stuff. You want to be convenienced or do you want to be accurate? The answer is accurate. So let's hold on to the exact value here. Before I proceed, does anyone have a question about finding k? Okay. Ooh, a question. Let's see what it is. No. Okay. Sebastian, what do you mean by that? Second seemed easier. The bottom part. Well, we're not done with it yet. We are still, yeah, we're still working on it. We're at the midpoint, if you will. Yeah, it's still going. Yes. Okay. All right. So we were not asked to find the rate of decay, which is what we found here when we found k. We were asked if 30 grams is present now, how much will be present in 300 years? Okay. Now is where we're going to go back to our initial equation. We're going to kind of move up this way. A equals A sub naught, e to the kt. So we use the half-life formula to determine the value of K. And now we're just going to use this general model for growth and decay to determine the amount that we're going to have left over after 300 years. Okay, now you're given some information here. If 30 grams is present now, so we're going to use that as the initial amount now. And then when we talk about 300 years from now, that's going to be the time t. Now, our value of K is going to be this special exact value that we found, the natural log of 1/2 divided by 7/10. So we'll leave that there. So e to the natural log 1/2 divided by 7/10. And you can simplify. Oh, whoops. You know what? I was going to say you can simplify, but no, because I read it one way, but I was not writing it. Let's see. It's the natural log of 1/2 divided by 7/10. I'm even just going to put some brackets on that. So that's e to the k t. T is going to be 300 years. And that is going to tell us the amount in 300 years. So we have 30 grams now. We know the rate of decay is the natural log of 1/2 divided by 7/10. And we want to figure out how many grams will be left after 300 years. Does anybody have a question about this formula or how we entered the data? Okay. Now all we have to do is evaluate. So I am going to put this in my calculator. I don't know. It seems about the same. Okay. 30 times e to the natural log of 1/2. If you prefer a decimal, fine. 0.5 is the exact same as 1/2, so totally fine. Make sure you close your parenthesis because you want to make sure that you're not dividing by 7/10 inside the log. And then we can multiply by 300 because what your calculator is going to do is it's going to take the natural log of 1/2, divide it by 7/10, and then multiply it by 300, which is completely fine. And then we're going to see what we come up with. Now remember, the amounts that we were talking about were listed in grams. 30 grams are present now. How much will be present in 300 years? So that means the amount that will be present in 300 years is about 22.38 grams. Make sure that you label your answer with a unit. On your test, if you don't put a unit on this, you will lose points. You must use a unit. Grams. Jimena got 0 when she plugged it into her calculator. How did she get that? I'm going to guess, Jimena, that you have something missing in either a parenthesis or let's see if I can replicate. Whatever it was probably small enough that it went down to 0. To the natural log. No. I don't know if I can replicate what you did, Jimena. I'd be able to. Let's see. Oh, you figured it out. All right. Wonderful. So I didn't have to do anything crazy. Oh, I figured it out too. It looks like you divided inside your log instead of dividing the log by 710. Okay. Anyone else? Questions on this one? Is this the real half-life for silicone? I think so. Oh, Jimena said she multiplied by 3 instead of 300. Oh, well, that'll do it too. I think it is, Beth, but you can look that up. I don't think you would be given false numbers on notes. Usually when I pull exercises for your notes, I pull them from like random other sources. I don't make them up. So I would not have made up a random half-life unless it was for some weird thing that I made up, like Zumibicon or something, not silicone. Okay. So this is a model of a half-life problem. If you see a half-life problem on your test, prepare to do this in 2 parts. Use the half-life formula to solve for the rate of decay. Once you find that, use the given information with your initial function for growth and decay to solve for your final amount. All right, you've seen it done. This is a good one if you're needing to make it more vibrant in your notes, you know. Feel free to call it out with a big star so that you can find it easily when you're taking your test or when you're working on your homework and you're practicing for your test. Okay. The last thing we're going to talk about in 4.5 is a logistic growth model. Sometimes I skip this. It's pretty short though, so I figure we might as well just talk about it. It's not something you're going to see a whole lot, but you might see it again. So I guess skipping it would be maybe not the best idea. The mathematical model for limited logistic growth is given by A equals C over 1 plus A e to the negative BT. A, B, and C are constants such that C and B are positive. So there's not much you're going to have to do with these other than just answer some questions using a given model, but you're not going to have to set up the models yourselves. Okay. So, for instance, the logistic growth function f of t is 680 divided by 1 plus 21.7 e to the negative 0.15 t, describes the population of a species of butterflies T months after they're introduced to a non-threatening habitat. How many butterflies are expected in the habitat after 10 months? Now, you're not given a whole ton of space on these. Again, for a reason, they don't require a whole lot of work. Remember that T is the number of months after they're introduced to the non-threatening habitat. So if T represents months, and you're trying to figure out how many butterflies are expected after 10 months, then you're just trying to find F of 10. And this you can plug into your calculator. Just don't forget that you have a negative in the denominator on your exponential expression. Let's see if I can make this better. Oh, a little bit. All right, 680 divided by, and as soon as you start to enter the denominator, start a parenthesis because you have 2 terms in the denominator. 1 plus 21.7 e to the negative 0.15 times 10. Enter. And you get approximately 116 butterflies. Yet normally we would, well, I guess if we're talking about butterflies, we should round to the nearest butterfly. It doesn't really make sense to talk about a fraction of a butterfly. It is a non-threatening habitat, after all. 116 butterflies. Questions about A? Okay. Wonderful. Now, B is a little trickier because you've never been asked for a limiting size of the butterfly population. What is the limiting size of the butterfly population that the habitat will sustain? Now, this is tricky, but I want to show you a couple different ways of doing this. I think the easiest way will be to look at this function in your graphing calculator. But really what we're trying to determine is, if we just let T go on and on and on and on, I mean, you started out with, well, it didn't actually tell you. We have to find that and see. You started out with a certain number of butterflies, and after 10 months, you found that you had 116 of them. You know, maybe let's start with C and then move to B so that we can get a good idea of what's happening. Let's do that. We'll come back to B. I think C will be helpful here to finding B. C, how many butterflies did we have when we introduced them to the habitat? That would be at time equals 0. Remember that T is the number of months after they're introduced to the non-threatening habitat. When T is 0, that will give you the initial amount. So F of 0 is 680 divided by 1 plus 21.7 e to the 0. E to the 0 is 1. Therefore, it's going to be 22.7. So you'll have 680 divided by 22.7, which is approximately 30 butterflies. Okay. Now, it is important here that the distinction was made that the habitat is non-threatening, because, for instance, if you're talking about animals in the wild, normally you talk about rabbit populations and you only think about the rabbits growing and growing and growing until some natural predator comes around and kills them off. However, when you're talking about some animals in the wild, for instance, like elephants, the numbers a lot of times are not increasing, they're decreasing because there are a lot of predators around that are trying to kill off the elephants. So the fact that the butterflies are in the non-threatening habitat should indicate to you that they're thriving and growing and they're not just going to be randomly dying off. Their population is not going to decrease. You started out with 0 butterflies, and then after 10 months, you had 116 approximately. So you have this growing amount of butterflies. The question is, as time goes on, you started at 0 months, then you evaluated at 10 months. At some point, the habitat cannot sustain, for instance, like 1 million butterflies. It cannot happen. You only have space for so many. So the question is, what is the maximum number of butterflies that you can have? So the way you're going to think about that is, as time continues to move on, like as the number of months gets larger and larger and larger and larger, what happens to F of T? The size of this butterfly population. Let's go ahead and look at this function in our graphing calculators. So we have F of T, and we're going to use X here instead of T just for purposes of our graphing calculators. 680 divided by 1 plus 21.7 e to the negative 0.15 x. Don't put in T. We're not in parametric mode. And I'm going to make sure I entered this correctly. 1 plus 20.7 e to the negative 0.15 x. Okay. And now I'm going to format my table. Remember, we do that using table set. So second window will get me up to table set. I'm back on auto because I found that helpful for something else I was doing. I'm going to switch my independent variable back to ask because I want to look at really large values of x here to see what happens to f of x. Now we'll go to the table. Now, look what happens if we talk about 0 and 10. Those are the numbers that we found when we evaluated f of 0 and f of 10. We found 30 butterflies and 116 butterflies. Well, what happens as these values continually get larger? Like, what if we looked at this after 100 months? 680 butterflies. What about 1,000 months? 680 butterflies. 10,000 months. Again, we're back to 680. So you're seeing that for large values, you're not going to get a value that's larger than 680 butterflies. I mean, even let's say we chose a number between 10 and 100, you can see the number start to increase, but it is really getting, it increases quickly up to 680, and then it cannot sustain anymore. Now, depending on what kind of math you've had in the past, you might have looked at what happens as the value of t approaches infinity. And you would have said, all right, well, it must be the case then that 680 divided by 1 plus 21.7 e to the, let's say, infinity, or it'd be negative infinity, sorry, because we have a negative there. And then you would just be looking at that value. So this is actually pretty advanced. This is something that you'll be doing in calc, but it's kind of an interesting question for this particular author to include in this text. What you're looking at here is thinking about this value for your exponential function, e to the x. Let's go back here. Sorry, I forgot to put this in my view. I'm graphing e to the x. So when you are looking at the graph of e to the x, graph, not table, notice that for e to the x, as x approaches values of negative infinity, y is approaching 0. So what happens here is you end up with 680 divided by 1 plus 21.7 times 0, which is just 680 over 1, which is approximately 680 butterflies. I don't know if I would ask something like that on an exam. I probably wouldn't, but I really think it's a good question. It's a good thing to talk about, and some of you will be ready for it and some of you will not be ready for it. And it's always good to kind of be thinking about these things. Oh, sorry. You know, I had the chat open, and when I had it open, it wasn't beeping at me. Michael, what were you getting 8991.217 for? Because I'm worried, Michael, that you that something got entered wrong. The silicone problem? Sorry. How did we get way past that? I did not see your tab. This is why I always try to keep it closed. Otherwise, it doesn't beep at me. Michael, were you talking about the second part of the silicone problem? Sorry, I'm going to go back to it just because I feel terrible now. Are you talking about this part? Okay, so for this problem, when you enter it into your calculator, you might have an older TI also. It must be the case that maybe it could be that your 300 is not inside the exponent. It could be a lot of things. Let me see what happens when I do that. Yeah, look at that. Look at that. How do I keep producing everyone's errors? I'm like really on point this semester. Michael, your 300 is not inside your exponent. So make sure that if you do have an older calculator, you're just going to have to make sure that you don't close out your parenthesis on your exponent before the 300's in there. So notice how mine, it's in the exponent. this is what you'll get 8991 if it's not in the exponent. Were you able to figure out how to put it into the exponent? I so wish I still had my old 83. Because let's see, you would be entering 30 e to the natural log 0.5. Let's see, e to the, if you have an older calculator, it would look like this. E to the natural log 0.5, close parenthesis, divided by 710 times 300, close parenthesis. So if you have an older calculator, I think it looks like this. I can't remember. It's been a while since I've seen it. Okay. Awesome. Okay, good. Wonderful. So that was that. And then let's see, back to our butterfly problem. Beth says the real half-life for silicon-32 is around 150 years, but math problems that claim the half-life is 710 are super common all over Google search results. Interesting. I wonder why. Interesting. I actually don't even think that I put these notes together. I think Vicki Walker wrote this page. I don't know if anyone knows Mrs. Walker. She's wonderful. Okay. I don't even know. Maybe she got it from someone else. All right. I'm not too worried about this. No big deal. That's just sort of like a derive thing, which I'm not going to ask you on your test. Okay. Let's review because you have a test, I think, Wednesday. And should we vote? Maybe I should have added that. Oh, I should add that to the Pear Deck slides because then we could get a real-time answer for the voting process that we're about to go through. Let's do that. I will add it into the pair slides really quick. I'm so excited. Okay. New slide. Let's see, can I move it? Not used to doing all this stuff in Google Docs. I'm not a big Google Doc fan. Should we have so the question is, should we have the test on Wednesday, 10/28, or Monday, 11/2? Now I'm going to give you choices. That will be Wednesday, 10/28, or Monday, 11/2. Okay. And then we'll start it up and we'll see if we can get people voting. Now, here's the deal. I told you before, I'm going to mention it one more time just to make sure that everybody understands. Let me come back to my meat here. Okay. I think we should have the test Wednesday. I've said it before. I'm saying it again. I think it'll be better for you because you'll get it out of the way and then have a fresh, clean mind heading into chapter 5. If we wait until Monday to take the test, then yes, technically you'll have the whole weekend for it to loom over you and you can study or not study all weekend and then worry about it Monday. But the thing is, we're going to have to start chapter 5 on Wednesday, like 2 days from now. And it won't be on your test, but we're going to spend class time talking about it. And you might fall behind because maybe you'll focus so much on chapter 4 that you won't think about chapter 5. And then all of a sudden you're scrambling to do the initial stuff that we talked about in chapter 5. Chapter 5 has nothing to do with exponential functions or log functions. It's all about systems of equations. And we actually do 3 sections from chapter 5 and I think 4 from chapter 6. And we combine them together. So it's all about systems of equations and matrices. So nothing to do with exponents and logs. So I'm going to put it out there, and I'm going to strongly suggest you just take the test Wednesday and be done. But if the class votes and decides to take the test on Monday, then that's fine. We'll do it Monday and we'll start chapter 5 Wednesday. Does anyone have a question before we vote? Okay. So let me get your little slide thing. I looked at GimKit, by the way, and it costs money. So I'm just, I'm totally out of professional development funds, and something I bought in the spring, they charged me for in the fall. And I'm just like, great, because I needed that money for something else. And I had spring money. I don't know what's going on. Anyway, let's see. First world problems, right? Okay. There is a 30-day trial of it, so maybe just to see this. I mean, really? Well, I think I don't know, it said add a teacher account, and then it said like you get the first 30 days free, and then it's like $4.99 a month, and I'm just like, if I'm not going to use this, I don't want to pay for it. I wonder if a student account, just because you're not creating stuff, you're just logging into it, it's free. I don't know. Okay, let's see. I don't know. Nobody likes Pear Deck. I only like it just because it went into my Google Suite so nicely. Interesting. Okay. What if I say that start lesson allows you to get all the Power Deck engagement? Oh, yes. Do this. Okay. Okay, so your job is to go to joinpd.com. Let me share my screen here so you can get the code. The code is ZAGBLL. They are lowercase L's, not uppercase I's. And then I have review questions for you after you vote. So then we can go through a review without any bells and whistles of earning money and all kinds of crazy things. I know, totally not fun. Okay. All right, I got 11 students. How many am I expecting? 23. All right. Everyone's so fast today. I'm only missing 5 students. Now, if you want to vote, you better get onto this thing. Otherwise, you won't have a say. And elections have consequences, as we know. All right, I'm still waiting on 5 students. Joinpd.com. Oh, Beth is trying. Okay. Well, that's good to know because I don't know who the students are. And we certainly want Beth to have a say. She's a very involved member of our class. Okay, we got 20. Beth, are you in now? Excellent. Okay. 21. All right. For the 2 stragglers, I give you like 1 minute. I'm going to wear my gloves next time, I think. I'm just so cold. I just have to keep warming my hands. I need like one of those muffs or something. Jeopardy theme plays. I love Jeopardy. Maybe we'll have to look into this. All right, all right, all right. Just one more thing I have to do, you guys. All right, I'm going to start. Should we have the test on Wednesday, 10/28, or Monday, 11/2? Now, I'm presenting this to you, but you should be on your screen seeing a multiple choice option. I guess I don't need to present to you anymore because you're doing this on your screen. There we go. Now, if I show responses, oh, I guess maybe I should present so that you can all see the responses. But see, I want to wait until everybody has voted because I don't want some views to sway other views. All right. Oh, good. We got all 21 respondents. What do you guys think happened? What did we vote for? Oh, not a window. Chrome tab. Yes. We voted for Wednesday. All right. The Wednesdays have it. 2/3 of us chose Wednesday. All right. Wednesday it is. Excellent. Okay. So the test is Wednesday. That's great. That means I need to get cracking on my test writing because all weekend I was like, oh, I should do this. And then was like, I don't really feel like doing this. Now I have to. I mean, if you don't wait till the last minute, what's the point? Okay. All right. Well, I have for you, let's see, it says guided class. Okay. So I showed this. What does lock screens mean? Does anyone know what lock screens means? Clearly I need to do more research. High responses. Okay. Oh, you can't change the answer. Oh. Gotcha. Very good. You guys are so helpful. Okay. All right. So let's do some review. I thought about putting you in breakout rooms, but I thought, are they really going to talk about how to do math problems in the breakout room? Probably not. Okay. So next slide. Now this one I didn't actually have a student input for. I just want you to work on it because I thought it would be, I don't know. Oh, good. See, no one would do this in breakout rooms. Okay. Because I think it's good review. So your job is to jot down the graph of f of x equals 1/2 to the x. And then if you're like, wait a second, I don't remember how to graph log base 1/2 of x. Well, you know that they're inverses. Therefore, their coordinates are switched. So I'm going to give you, let me set my timer here. How long do I think you need? 4 minutes. I'm going to give you 4 minutes to graph these functions. Go. Act like you're taking a test. You're under pressure here. All right, I lied. 3 minutes because I didn't realize we were running out of time. Well, not really, but I want to have time to review more interesting things. Okay. Now, when you're graphing your exponential function, start out just by using your standard values and evaluate your function at those values. You should have a table written down for different values of x, and you should start to get a list of points. -2, 4. Oh, -1, 2. 0, 1. 1, 1/2. And 2, 1/4. And you can start to see the behavior of your exponential function. Remember that the coefficient is less than 1, but greater than 0. So it must mean that your graph is going down as it heads from left to right. So this is your function f of x. And then remember that g of x is just the inverse. G of x is log base 1/2 of x. So you're going to flip-flop those points. Instead of having a point at -2, 4, you're going to have a point at 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. You could always use the change of base formula to check this in your calculator, but on your test, when I ask you to graph, this is what I'm looking for, a table of values. All right, so 4, -2 is right here. 2, oh, I did not do 4, -2. I did 2, -2. 4, -2. 2, -1. 1, 0. 1/2, 1. And 1/4, 2. Kind of goes up like this. Remember that these are inverse functions. A log function has a vertical asymptote as the y-axis. So the domains for f of x is going to include any value of x. And for g of x, your domain is going to include only positive values of x. So only values to the right of the y-axis. Okay. That would be how to graph f and g. Those are inverse functions. So graph the exponential, invert the points to get the log function. Now let's see here. So if I flip through the slides, you guys see what's coming up next on your screen? On a test, do we need a table if I plug the equation in my calculator? Yes, I know that you know how to use your calculator. I want to know that you know how to do it by hand, Benjamin. So yes, show me your work in a table. If the table comes out of your calculator, there's nothing I can do about that. If the values are exact, and I would never know the difference. But if they're values like 0.2574, then I would be like, where'd that come from? Okay, I'm not going to do this investment problem because I feel like you guys are pretty good with those. Oh, here's a good one. Evaluate the expression without using a calculator. So you guys are seeing this screen, right? Log base 3 of log base 8 of 8. Yes? Yes. Okay, excellent. All right, evaluate this expression. It shouldn't take you very long. Oh, and this is enter a number, not multiple choice. Interesting. Seeing all kinds of responses here. Okay, when I click show responses, does it show on your screen? No. Okay. Wonderful. Got about half of you here. Okay. Log base 3 of log base 8 of 8. Remember, you're asking yourself, first things first, you must start on the innermost function. You're asking yourself, 8 to what power is 8? So that would be 8 to the first gets you to 8. Because you have 8 to the first equals 8. So now you're asking yourself, log base 3 of 1 is what number? That means that 3 to what power equals 1? And we know that any number to the 0 power equals 1. I saw a lot of zeros in there. Not everybody, but I saw a lot of zeros. So 0 is the correct answer. Any questions on that one? Okay. Let's do that. Let's see. Equation that I was saying I did a similar one with Nancy. The domain, just set it to be positive. I think we could do that. That's a pretty regular old expand. We'll come back to it if we have time, or stick around for the office hour and we'll do the rest of these. But I did want to go over this one. 3 to the x plus 4 equals 7 to the 2x minus 1. And this might take you the next 5 minutes at least. Let's see. right, if you are still working, that is okay. If you wanted to stick around for the office hour, we'll do more. Otherwise, I wanted to make sure I got this one done in class. 3 to the x plus 4 equals 7 to the 2x minus 1. Looks like we have 9 correct responses. Excellent. So what, a third of you? More. Okay. When you're solving an exponential equation, if you can't equate the bases, which in this case you can't, there's no way you can write 7 with the base of 3, you're going to have to take a natural log on both sides. And remember, the reason you want to do this is because you want to get the variables out of the exponents. The only way you can do that is by taking a natural log on both sides. Now your next step is to take the exponents and pull them out in front of the log using the power property for logarithms. Make sure that when you move those exponents in front, that you use parentheses to enclose both terms. Now that you've done that, remember your goal is to solve for x. You've got x's inside different expressions here, so we're going to need to split them up. Distribute these into your logarithms. So you'll have x natural log 3 plus 4 natural log 3 equals 2x natural log 7 minus 1 natural log 7. Now remember, again, your goal is to solve for x. I want to get all of the x's to one side of the equation, and anything that doesn't have an x on it needs to go to the other side. Now, I don't care how many steps you do this in. I'm going to do it in 2 just because I don't want it to look confusing if I do it in 1 step. So I'm going to subtract x ln 3 from both sides. And everything else stays the same. The only difference is I've moved that x ln 3 term to the other side. And remember, no matter what, you cannot combine these two natural logs together. 2x ln 7 minus x ln 3, they're not like terms. They would both have to have the natural log of 7 on them. They don't have that, so you cannot combine them. So let's go ahead then and get the non-x's to the other side by adding ln 7 to both sides. And remember, you cannot combine those. They're just going to be 2 separate terms. Now your goal is to solve for x. That means that you need to get the x by itself as a separate factor. Keep the left-hand side as is. On the right-hand side, factor out the x. If you factor it out, that's going to allow you to divide out anything that doesn't have the x on it. So just factor the x out of both terms on the right-hand side. Now I'm going to write this one more time so it looks clear when it's done. To get x by itself, divide both sides by 2 natural log 7 minus natural log 3. And you have x equals 4 ln 3 plus ln 7 divided by 2 ln 7 minus ln 3. Whoops, sorry. And then you're going to get a decimal approximation for that. And you're going to be very careful when you do that with your parentheses. There's going to be a lot going on here with your parentheses. So you have in parentheses 4 natural log 3, close off the parenthesis on your natural log, plus natural log 7. Now close off the natural log, close off the numerator. Make sure that your open parentheses equal the closed parentheses. Divided by open your parenthesis, 2 ln 7, close, minus ln 3, close the natural log, close the denominator. And this will give you approximately 2.27. So all of those 9 people, 10 people now, were correct. Okay. Stick around if you want to do some of the other review slides. Otherwise, we're going to have our Chapter 4 test on Wednesday, sections 1 through 5. So 4.1 through 4.5. Today, I covered 4.5. Someone said that they wanted me to give out the page numbers for the sections that I covered. Maybe I'll put that in the notes for the YouTube links when I upload them to D2L. But today I covered pages 519 through 528 in your book. So I can put those in the YouTube links that I upload to D2L. All right, so stick around if you want more review. Otherwise, your test is Wednesday. Show all of your work.